Hello there, and welcome to the Sleepy Space Channel. A ship could probably leave. That is not the difficult part, and it is not what makes the crossing to the nearest star so sobering. The difficulty is that nobody who leaves is the one who gets there. At the fastest speed anyone has seriously proposed, the journey takes 4 decades. At the speeds we can actually reach, it takes 6,300 years, which is longer than the entire written record of our species. Between those two numbers sit the engine nobody knows how to build, the fuel that outweighs every atom in the universe, the radiation that arrives from every direction at once, and a body that quietly begins taking itself apart. Over the next 2 hours, we will work through each of them in turn. If you find these explorations worth your time, a like or a subscribe helps the channel reach others who do. Thank you for being here. But for the next 2 hours, none of this is anything you need to carry. Nobody is asking you to go. Settle in. Let your shoulders soften. Let your breathing slow. Let the day fade away behind you. Let's begin. Part 1. The number that sounds small. The nearest star to our Sun sits 4.24 light-years away. That number arrives sounding almost manageable. It has a decimal point in it. It is the kind of quantity you could write on a chart and trace with a finger, the kind of distance that seems to belong to the same family as the distances we already know how to cross. It does not sound like a wall. It sounds like a figure. It is 25 trillion miles. And the strange part, the part that rarely gets said plainly, is that the distance is not the thing that would stop you. The distance is only the first of the walls, and it is by some margin the simplest one. Everything else waits behind it. Start with the destination itself, because the destination is not what most people picture. The nearest star system is not a star. It is 3 of them, held together in a quiet hierarchy, sitting low in the southern sky in the direction of a constellation called Centaurus. 2 of those stars form a close central pair. One is a yellow star, very slightly larger and slightly brighter than our own Sun. The other is a cooler orange companion putting out roughly half the Sun's light. The 2 circle each other on a stretched ellipse, taking about 80 years to complete one turn, swinging from something like Saturn's distance apart at their closest to well beyond Neptune's distance at their widest. The 3rd star is a faint red dwarf, far out from that central pair, roughly 1/5 of a light-year away from them, on an orbit that takes something in the region of 500,000 years to complete. That red dwarf is the closest single star to our Sun, and it holds the title by a small margin. It is also far too dim to see with the unaided eye, which is its own quiet oddity. The nearest star to us is a star that nobody has ever looked up and noticed. Now the unit, because the unit is where the number stops being friendly. Light moves at approximately 186,000 miles per second. In 1 second, light crosses a distance roughly equal to circling the Earth 7.5 times. In 1 minute, it covers about 11 million miles. In 1 year, it covers about 5.88 trillion miles, or roughly 9.46 trillion kilometers. That is 1 light year. It is a unit of measurement large enough that the human mind cannot hold it as a quantity. We can hold it as a word. We say the words, we write the number, and then we move on, because staying with the number too long produces a sensation most people would rather not sit inside. 4.24 of those units comes to roughly 25 trillion miles, or about 40 trillion kilometers. There is no useful everyday comparison available. The number is not large the way a mountain is large. It is large in a way that defeats comparison entirely. There is one model that helps, a little. Shrink the entire solar system down until the distance from the Earth to the Sun is the length of a single sheet of paper. On that scale, the Sun is barely a hand's width from where you are standing. The whole of the planetary system, out past the ice giants, fits comfortably within a few paces. And the nearest star sits about 230 feet away at the far end of a long building. Everything else in the galaxy extends out from there for millions of miles. The paper shrinks the numbers. It does not change them. And even on that scale, we have never once managed to cross the sheet of paper. It is worth saying how we know the number at all, because we did not go and measure it. The distance comes from parallax. Watch a nearby star carefully across 6 months, while the Earth moves from one side of its orbit to the other, and the star appears to shift very slightly against the far more distant background. The size of that shift gives the distance directly by simple geometry. For the nearest star, the shift is under 1 arcsecond, which is roughly the apparent width of a coin seen from 2 miles away. That is the entire basis of the figure. Everything else we believe about the gap rests on a measurement smaller than the thickness of a hair held at arm's length. Consider the fastest object our species has ever built. It is a probe designed to study the Sun, sent to dip repeatedly into the outer atmosphere of our own star and measure the fields and particle winds streaming outward from it. At its closest solar approach, it reaches speeds of approximately 430,000 miles per hour. That is about 190 kilometers every second. It is fast in any ordinary sense of the word, fast enough to cross a continent in about 20 seconds. Fast enough to circle the Earth in under 4 minutes. There is a qualification attached to that speed, and it matters. That velocity is not an engine's achievement. It is gravity's. The probe is falling. Its speed is the product of a carefully shaped trajectory that uses the Sun's own pull to accelerate it, and it only holds that speed at the very bottom of the fall, for a matter of hours, before climbing back out and slowing again. No rocket carried aboard it could produce that velocity. And nothing about its design points outward, away from the Sun, toward anything. But take that speed anyway. Point it directly at the nearest star and let it run continuously, without slowing, without stopping, for as long as it takes. It would arrive in approximately 6,300 years. Consider what 6,300 years actually means. The Great Pyramids were completed roughly 4,500 years ago. The entire written record of human civilization, from the first pressed clay tablets to the device this is playing on, spans perhaps 5,000 years. A journey to the nearest star, at the fastest speed we have ever achieved, would outlast the whole of recorded history by more than 1,000 years and still be underway. It would still have most of a millennium left to run. There are already objects on their way out. 5 spacecraft are currently on paths that will carry them free of the Sun's gravitational hold entirely. They are traveling at somewhere between 11 and 17 kilometers per second, which is roughly 35 to 38,000 miles per hour. That is an order of magnitude slower than the solar probe's peak. None of them is aimed at anything in particular. At those speeds, a crossing of 4 light-years would take on the order of 70 to 80,000 years, and the nearest of them will not pass within a few light-years of any star for tens of thousands of years yet. They are not going anywhere. They are simply leaving. To turn the crossing into something a civilization could plausibly attempt, the speeds have to change by orders of magnitude. To reach the nearest star within a single human lifetime, say 100 years, a spacecraft would need to sustain roughly 4% of the speed of light. That is about 26,700 miles every second. To do it inside a single working generation, closer to 40 or 50 years, the ship would need to approach a tenth of light speed. These targets are not arbitrary. They are the thresholds below which the crossing stops being a mission and becomes something closer to an exile. Set that against where we are. The solar probe's peak velocity is 0.064% of the speed of light. If the speed of light were a mile, that probe, the fastest thing we have ever made, would have traveled about 3 feet of it. And there is one more complication, which is that the target does not stay where you left it. The stars are not fixed. The Sun and its neighbors orbit the center of the galaxy at roughly 220 kilometers per second, and they do not travel in formation. Each one carries its own motion, inherited from the cloud it formed in, and modified by every close pass since. The nearest star system is currently approaching us. In something like 27,000 years, it will make its closest pass at a little over 3 light years, and then begin to recede again. Over the timescales a slow crossing would require, the destination is not a fixed point. It is a moving one, and the navigation set at departure would be wrong long before arrival. So that is the distance. That is only the distance. It is a number that sounds small, and it is the easiest thing on the entire list. It contains no engineering, no biology, no chemistry, no question of energy or endurance or human patience. It is just the gap, sitting there, entirely uninterested in being crossed. And we have not yet said a word about what fills it. Part 2. What fills the gap? Most people, asked to picture the space between the stars, picture darkness. That is accurate as far as it goes. But darkness is a description of light, not of matter. The space between the stars is not empty the way an unoccupied building is empty. It is empty in a way that has no comfortable analogy anywhere in ordinary experience. The average density of interstellar space is roughly 1 atom per cubic centimeter. Overwhelmingly hydrogen, with a fraction of helium and a trace of everything heavier. 1 atom, in a volume about the size of a sugar cube. For comparison, the air in an ordinary room contains approximately 27 million trillion atoms in that same volume. The best vacuum chambers ever built on Earth, the ones used for the most delicate physics experiments, are still many orders of magnitude denser than the space a ship would cross. This is not thin air. It is not trace air. It is a vacuum complete enough to destroy an unprotected biological system within seconds. The fluids of the body reach their boiling point at body temperature, not because of heat, but because of the absence of pressure holding them liquid. The lungs empty outward rather than inward. Useful consciousness lasts somewhere between 9 and 12 seconds. There is no version of this that is survivable without a machine between you and it, and the machine has to work perfectly, every second, for as long as the crossing lasts. The medium is also not uniform, which is a complication that gets less attention than it deserves. The Sun is currently drifting through a small, warm wisp of slightly denser gas, a local cloud a few light-years across. That cloud sits inside a much larger and thinner cavity, a bubble in the interstellar medium several hundred light-years wide, carved out long ago by ancient stellar explosions. The nearest star lies inside the same cavity, which is a piece of good fortune. But a ship crossing 4 light-years would pass through more than one density regime, and the numbers it encounters are not constants it can design around in advance. The map of what lies along the route is far coarser than the route would require. There is also dust. Interstellar space carries grains, silicate and carbon particles, typically a fraction of a micrometer across, at densities of roughly 1 grain per million cubic meters. At walking pace, those grains are nothing whatsoever. At a fraction of the speed of light, they are not nothing at all, and we will return to what they become. A few other properties of the medium are worth having in mind, because they define the environment a ship would spend its entire operating life inside. It is not at absolute zero. The residual warmth of the early universe fills all of space at roughly 2.7 degrees above absolute zero, and that is the temperature anything far from a star eventually falls toward. It is genuinely silent, in the strict sense, because there is no medium dense enough to carry a pressure wave. An event of any violence occurring nearby would arrive as light and particles only, with no sound attached to it at all. And it is threaded with magnetic fields, weak by laboratory standards at a few millionths of a Gauss, but coherent across enormous distances, steering the paths of the charged particles that will matter a great deal later on. There is also a boundary to cross on the way out. The sun inflates a bubble of its own wind against the interstellar medium, and the outer edge of that bubble sits somewhere beyond 100 times the distance from the Earth to the sun. Any outbound ship crosses it within the first couple of decades of the voyage. But the sun's gravitational reach extends much further, out through a shell of icy bodies that may run a light year or more from the star. Which means, oddly, that a ship might spend the first quarter of the crossing still technically inside the sun's own system, drifting through the outermost debris of the place it left. But the deeper feature of the gap is not what it contains. It is what it forecloses. Every mile traveled outward roughly doubles the cost of coming back, because the return requires the same acceleration budget all over again, from a standing start, paid with whatever mass survived the outbound leg. This is the arithmetic that shapes everything else. At a hypothetical midpoint, a ship would be 12.5 trillion miles from home, with 12.5 trillion miles remaining, and the two directions would be equally impossible. There is no point on the route where turning around is easier than continuing. There is no point where help becomes reachable. What that means in practice is that the crossing offers no forgiveness. There is no resupply. There is no rescue. There is no spare part that was not packed at departure, no repair that cannot be improvised from what is already aboard, no medicine that was not carried or manufactured en route. Every problem that arises across 25 trillion miles is a problem that must be solved with the inventory of a single loading, made decades or centuries or millennia before the problem announces itself. The communication ledger tells the same story in a different currency. Signals travel at the speed of light and no faster, and the delay grows with distance in a way that changes the character of the mission at each step. From the Moon, the lag is about 1.25 seconds each way, which is noticeable but conversational. From Mars, it runs between roughly 4 and 24 minutes each way, depending on where the two planets sit in their orbits, which means conversation ends and message passing begins. From Jupiter, it is 35 to 53 minutes. From the outer boundary of the Sun's wind bubble, around 21 hours. And from the nearest star, it is over 4 years each way. A question asked from the ship is answered, at the absolute best, more than 8 years later. Past a certain distance, mission control stops being a control. It becomes an archive. The people on the ground are not directing anything. They are recording what already happened and sending back replies to situations that resolved themselves, one way or another, years before the reply arrives. Signal strength is a separate problem, and in some ways a harder one. Radio power falls with the square of distance. Communicating across 4 light-years at anything like a useful data rate would require transmitting power, antenna sizes, and receiver sensitivities beyond anything that has ever been built. The current deep space network struggles to pull faint signals from probes a few light-hours away. The communication system for a genuine interstellar mission does not exist even as a serious design. It is one of the quieter missions in almost every proposal. The consequence is that crew autonomy stops being a philosophy and becomes a physical fact. Beyond roughly the distance of Mars, the round-trip delay already makes real-time guidance impossible, and the crew becomes the highest authority in its own environment for every decision that matters. Across 4 light-years, this is not a delegation of authority. It is a severance of it. There is no chain of command reaching back to Earth, because a chain of command requires that instructions arrive while the situation still exists. This is the design constraint that makes the crossing genuinely strange, and it is worth holding on to because it shapes every part of what follows. The difficulty is not the distance alone. It is that the distance is one-directional in practice. Everything about such a mission would be built around that fact. The redundancy philosophy, in which nothing has a single point of failure. The spare parts manifest, which must anticipate failures nobody has yet observed. The medical inventory, which must cover conditions that have never occurred. The food system, which must close its loop almost perfectly because a 2% annual loss compounds into starvation across a century. The social structure, which must hold together without any external pressure to hold it. All of it follows from the same fact, which is that after departure, there is no back. And there is something worth noticing about the medium itself, which is that none of it is directed at anyone. The near vacuum is not hostile. It is the ordinary condition of the universe, the state of almost everything, almost everywhere. Planets are the anomaly. Air is the anomaly. Warm rooms with breathable atmospheres and enough gravity to keep a person's feet on the floor are so rare that the universe has produced, as far as anyone has confirmed, exactly one of them. The gap between the stars is not an obstacle placed in the way. It is simply what most of the universe is, and the exceptions are what we happen to be standing on. The interstellar medium is also, and this is the part that quietly softens the whole picture, the raw material of every star that has not yet formed. The same near nothing a ship would cross is the stock from which future suns are drawn. Given enough time and enough gravity, 1 atom per cubic centimeter becomes a cloud, and a cloud becomes a cluster, and a cluster becomes a sky full of new light. The emptiness is not a permanent condition. It is a stage in a very long process, and the ship crossing it would be moving through the early draft of something else entirely. Part 3. The engine no one knows how to build. Before the radiation, before the biology, before any of the slower difficulties the crossing has waiting, there is a more fundamental problem. It exists before the ship ever leaves, before it is designed, before the first calculation is written on the first page of the first proposal. We do not know how to build the engine. That statement needs a qualification, because it is easy to hear it as a familiar kind of not knowing. We once did not know how to build a suspension bridge. We once did not know how to build a nuclear reactor or a machine that could hold a conversation. Those were problems of engineering. They had solutions waiting inside them, and patience and mathematics eventually found those solutions. Interstellar propulsion is not that kind of problem. The physics itself appears to be working against the attempt, and 70 years of serious study have not produced a door in the wall, only better measurements of how high the wall is. Start with what we actually have. Every human being who has ever left the Earth left on chemistry. The most energetic, practical chemical combination available is liquid hydrogen burned with liquid oxygen, and it produces an exhaust velocity of roughly 4.4 kilometers per second. In the standard measure of propulsion efficiency, that corresponds to a specific impulse of about 450 seconds. And here is the important part. That number is not an engineering limit that better design could raise. It is set by the strength of the bonds between atoms. Chemistry has been thoroughly explored. There is no undiscovered reaction waiting to double it. The ceiling is real, and by the standards of the crossing, the ceiling is very low. There is a ladder above chemistry, and it is worth climbing it slowly, because each rung tells you something. Ion drives and their relatives achieve exhaust velocities of roughly 20 to 50 kilometers per second, 10 times better than chemistry, but at thrust levels measured in fractions of a Newton. They are patient rather than powerful. They accelerate a spacecraft the way a steady breath moves a leaf, which is genuinely useful for reshaping orbits over months and useless for anything requiring urgency. Nuclear thermal rockets, which heat hydrogen in a reactor rather than burning it, roughly double the chemical exhaust velocity to around 9 kilometers per second. That hardware was built and ground tested in the middle of the last century. It ran. The program was cancelled for cost and politics, not failure. Nuclear electric systems reached the high tens of kilometers per second. Fusion drives, in concept, might reach several percent of light speed in exhaust velocity. Antimatter, in principle, approaches light speed itself. So the ladder exists. What matters is that the bottom 4 rungs are all still hopelessly short of what the crossing needs, and the top 2 rungs have never been built by anyone. The most credible interstellar engine ever seriously designed was a chain of nuclear explosions. The idea was studied in earnest for several years in the middle of the last century by a group that included some of the most capable physicists of its era, and it was elegant in the way that ideas are sometimes elegant before they collide with the world. A spacecraft would carry thousands of small nuclear devices. It would eject them one at a time behind a heavily armored pusher plate, detonate them, and ride each expanding shock forward. Thousands of detonations, one after another, across months or years of continuous acceleration. Behind the plate sat an enormous shock absorber, so that what arrived in the crew compartment as a series of hammer blows was smoothed into something closer to steady thrust. The mathematics, for a moment, very nearly worked. Estimates suggested such a vessel could reach roughly 3 to 5% of the speed of light, which puts the nearest star somewhere in the region of 1,000 years away. Still longer than recorded history. But for the first time, a number the mind could almost hold. And the concept had a property that nothing else on the ladder has, which is that it scaled upward well. Unlike chemical rockets, which get worse as they get bigger, this one worked better the larger the ship. Versions were studied from a few thousand tons up to 8 million tons, and the very largest of them were intended not as probes, but as vessels carrying populations. The program was cancelled, and it was not cancelled because the physics failed. It was cancelled because a treaty banning atmospheric nuclear detonations made the launch phase illegal. The most promising route anyone had drawn toward the stars was closed by an agreement about a different kind of fear entirely. It has never been revived. The shielding, the ablation of the pusher plate, the survival of the shock absorber across 100,000 detonations, all of it remained untested and remains untested now. A later study group spent years designing something different, an unmanned fusion-driven probe intended to reach the nearest star system within about 50 years, at roughly 12% of light speed. The design was a 2-stage vessel of some 50,000 tons, the overwhelming majority of it fuel, in the form of helium-3 and deuterium pellets ignited by electron beams at a rate of hundreds per second. 2 details from that design are worth carrying forward. The first is that the helium-3 was to be mined from the atmosphere of a gas giant, because there is not enough of it available anywhere nearer than that. The second is that the probe had no way to stop. It was a flyby design. It would cross the destination system in a matter of days, gather what it could, and continue outward forever. That second detail deserves to be stated as a general principle, because it applies to almost everything in this field. Slowing down at the far end costs, to a first approximation, as much as speeding up did at the near end. And it must be paid for with mass that has already been accelerated the entire way, which roughly squares the difficulty. Almost every interstellar concept that looks tractable on paper looks that way because it quietly assumes a flyby. The moment arrival is required rather than passage, the numbers change category entirely. The most discussed current proposal avoids the problem from another direction by removing the engine from the ship. A ground-based laser array illuminates a highly reflective sail a few meters across, pushing a gram-scale probe to roughly 20% of light speed over the course of a few minutes of acceleration. No fuel aboard. No engine aboard. The energy stays at home, where there is an entire planet to generate it. At that velocity, the probes reach the nearest star in about 20 years, and the data comes back 4 years after that. The requirements are where it becomes difficult. The laser array would need to deliver on the order of 100 gigawatts of sustained, coherent, phase-locked output, which is comparable to the entire electrical generating capacity of a mid-sized industrialized nation, focused into a single beam and held steady on a target a few meters wide as that target recedes to millions of kilometers. The largest laser facilities operating today produce enormous peak powers, but only for durations measured in quadrillionths of a second. That is a burst, not a beam. Sustained output at that scale has no current roadmap at all. The sail is no easier. The material must be extraordinarily reflective, extraordinarily thin, and able to survive an acceleration of tens of thousands of times Earth gravity for minutes at a stretch without tearing, wrinkling, or absorbing enough of the beam to vaporize. Absorbing even a small fraction of 100 gigawatts destroys it outright. And keeping the sail centered in the beam rather than sliding out of it is an unsolved control problem in its own right. All of which applies to probes the size of a coin. Nothing about the approach scales to a vessel carrying people. The energy required grows with the mass being pushed, and the difference between a gram and 10,000 tons is 10 orders of magnitude. There was one more idea, and it was the most elegant of all. Rather than carrying fuel, a ship would scoop interstellar hydrogen as it traveled, using an enormous electromagnetic funnel to gather the sparse protons drifting through the gap and feed them into a fusion reactor. The ship would fuel itself from the medium it moved through. It captured the imagination of an entire generation. Examined more carefully across the following decades, the physics refused to cooperate. At 1 atom per cubic centimeter, the funnel required to collect fuel at a useful rate would need to be hundreds of thousands of kilometers across, and the drag such a funnel produces, sweeping through even that near vacuum at a fraction of light speed, exceeds the thrust the collected fuel could generate. The ship slows down rather than speeding up. As originally conceived, it simply does not work. A version of it survives as a braking concept, using the same funnel purely to slow down at the far end, and that remains one of the few deceleration ideas with any legs at all. Part 4. The arithmetic that will not bend. There is an equation in physics that a great many people have seen and very few have sat with properly. It was derived more than a century ago by a provincial schoolteacher working alone by lamplight, decades before anything at all had left the ground. He was trying to answer a question that sounds simple. How much fuel does a rocket need in order to reach a given speed? The answer was not simple. What he found describes the relationship between a rocket's change in velocity, the velocity at which its exhaust leaves, and the ratio between the vehicle's starting mass and its ending mass. In plain terms, the faster you want to go relative to how fast your exhaust moves, the more of the vehicle's total mass has to be propellant. Not a little more. Exponentially more. The reason it is exponential rather than proportional is the heart of the entire difficulty, and it is worth stating slowly. Fuel has mass. Fuel that has not yet been burned must be carried and therefore accelerated by the fuel that is burning now. So adding propellant to go faster means adding propellant to accelerate the propellant. The curve does not rise steadily. It rises, and then rises more steeply, and then climbs into slopes the imagination cannot follow. You can see the shape of it in hardware that already exists. A large launch vehicle is roughly 90% propellant by mass sitting on the pad. 90%. And what that buys is a velocity change of about 9.5 kilometers per second, which is barely enough to reach low orbit around the planet it launched from. Every additional increment of speed costs disproportionately more than the increment before it. Now apply that to the crossing. To accelerate a spacecraft to 1% of the speed of light, which is about 3,000 kilometers per second, using chemical propulsion with its 4.4 kilometer per second exhaust, the equation produces a mass ratio that is not an engineering challenge at all. It is a statement about the nature of matter. Some calculations place the required propellant mass in the range of 10 raised to the power of several hundred times the mass of the payload. There is a comparison that ends this argument permanently. The observable universe contains roughly 10 to the 80th power atoms in total. Everything. Every star, every planet, every cloud of gas in every galaxy that light has had time to reach us from. The fuel requirement for a chemical rocket to reach 1% of light speed exceeds the mass of all of it, by a margin so large that the excess itself has no physical referent. And 1% of light speed still means a crossing of more than 400 years. This cannot be engineered around. Not with lighter materials, not with better manufacturing, not with more efficient tanks. Staging helps, and staging is why rockets shed their empty sections as they climb, since discarded mass no longer needs accelerating. But staging changes the arithmetic by factors, and the shortfall here is measured in hundreds of orders of magnitude. The chemistry itself forbids it, and no amount of cleverness applied to the vehicle changes what the chemistry permits. Nuclear energy improves the picture substantially without solving it. Fission and fusion release energy from atomic nuclei rather than from the bonds between atoms, and the difference in energy density is not marginal. It is roughly 7 orders of magnitude. Chemical propellants carry on the order of 10 megajoules per kilogram. Fission carries something like 80 terajoules per kilogram. Fusion, around 340 terajoules per kilogram. A theoretical fusion drive, using a reaction that has not yet been sustained in a net positive way anywhere on Earth, could produce exhaust velocities in the range of 10 to 20,000 kilometers per second. That is several percent of light speed coming out of the back of the engine. At those exhaust velocities, the mass ratios shrink from impossible to merely extreme. A few tens of times the payload mass, rather than a number with hundreds of digits in it. That is the difference between a problem and a nightmare, and it is the reason fusion appears in nearly every serious proposal, despite never having been made to work. Then there is antimatter, which on the arithmetic alone is simply the answer. Matter meeting antimatter converts to energy with complete efficiency. Every gram of antimatter annihilating with a gram of ordinary matter yields the full energy of 2 grams, which comes to roughly 90 petajoules per kilogram of antimatter. That is about 9 orders of magnitude above chemistry. Exhaust velocities approach light speed itself. The mass ratios become genuinely manageable. Journey times shrink from centuries to decades. If you were designing the crossing with no constraint except the rocket equation, you would use antimatter and you would stop worrying. The difficulty is supply. The total quantity of antimatter produced by human civilization across every particle accelerator ever built, across every experiment ever run, across the entire history of high-energy physics, amounts to something on the order of 15 nanograms. 15 billionths of a single gram. A crude vessel bound for the nearest star would require somewhere in the range of hundreds of tons of it. The distance between 15 nanograms and hundreds of tons is a factor of roughly 10 to the 19th power. That is not a production challenge that could be met by building more accelerators, or better ones, or a great many of them. Current production methods consume vastly more energy than the antimatter subsequently stores, by a factor in the billions, which means scaling up production is not merely slow or expensive. It is thermodynamically absurd with any technique anyone has described. You would spend the energy output of a civilization to store a fraction of it, and then have to spend it again. And it cannot be kept. Antimatter annihilates on contact with any ordinary matter, including the walls of whatever is holding it. Storage requires magnetic and electrostatic traps of extraordinary precision, continuously powered, held in hard vacuum for the entire duration of a voyage measured in decades. Antimatter has been trapped and held in laboratory conditions for periods of minutes, which is a genuine achievement and also a useful measure of the gap. Minutes for a few thousand atoms. Against decades for hundreds of tons. And a containment failure is not a fuel leak. It is the complete conversion of the stored mass into energy all at once, with nothing to absorb it. It helps to approach the same wall from the other direction, setting propulsion methods aside entirely and asking only how much kinetic energy the ship requires. Galaxies will continue to drift. The stars overhead may appear eternal, but the great web of galaxies is always in motion. Put in terms closer to home, it is many years of the entire electrical generation of human civilization, delivered into a single moving object. Doubling it in order to stop at the far end is, by that point, the smallest of the difficulties involved. There is a further cost that rarely appears in the headline numbers, and it is heat. Energy stored is not energy delivered. Every propulsion system loses a large fraction of its theoretical output to waste heat, and in a vacuum, the only way to shed heat is to radiate it. A ship producing gigawatts of propulsive power must also reject gigawatts of waste heat through radiators, and radiator area scales with the power involved. Which means the faster ship is also the larger ship, the more fragile ship, and the more massive ship. The heat problem feeds directly back into the mass problem, which feeds directly back into the fuel problem, which is where this part began. So the honest summary is this. The fuel problem has no solution for a crewed mission. Not a partial solution awaiting refinement, not a promising direction requiring investment. No solution at all inside any physics currently understood. Every proposal that appears to solve it does so in one of 3 ways. It shrinks the payload to something that cannot carry a person. It abandons the ability to stop. Or it assumes ready access to a substance we have, in the whole history of our species, produced 15 billionths of a gram of. The school teacher could not have known how high the wall was. He could only see its shape, the exponential curve climbing away from everything reachable, towards speeds the universe permits in principle and forbids in practice. Every decade of physics since has measured that wall more precisely. None of them has found a door. Part 5. The radiation that arrives from every direction. Even if the ship could be built, even if the fuel could somehow be found, there is still the matter of what the crossing does to everything inside it. And the first thing to understand is that radiation is not one phenomenon. It is a family, spread across a range of energies, arriving from different sources, damaging living tissue in different ways. The members of that family do not cancel one another out. They accumulate, and the defenses against one of them make another one worse. Begin with why the Earth is unusual. The planet generates a magnetic field, and that field deflects the majority of incoming charged particles around the globe, funneling the overflow toward the poles where it strikes the upper atmosphere and becomes the aurora. The light show is the damage, made beautiful and made distant. Above that sits the atmosphere itself, which provides the shielding equivalent of roughly 10 meters of water pressing down on every square meter of ground. Both of those protections are properties of a planet. Neither one travels with you. The first member of the family is the stellar wind. Our own sun streams charged particles outward continuously, in every direction, at speeds of roughly 400 to 800 kilometers per second. Mostly protons and electrons. This is the gentlest member of the family and the easiest to stop. A few centimeters of hydrogen-rich material handles the great majority of it, and any spacecraft hull already does reasonably well. It is also the only member that weakens with distance from the sun, which is a small mercy on an outbound journey. The second member is the one that shapes everything. Galactic cosmic rays are not rays in any ordinary sense of the word. They are atomic nuclei, stripped bare of their electrons. Protons, helium nuclei, and heavier nuclei running all the way up to iron, accelerated to extraordinary energies by the shock fronts of distant stellar explosions and by other violent events scattered across the galaxy. They travel at velocities approaching the speed of light. They carry energies millions of times greater than anything a particle accelerator on Earth can produce. And they arrive from every direction continuously, with no preferred source, no seasonal pattern, and no way to predict any individual one. What makes them the hard case is not the energy by itself. It is the penetrating power. A sufficiently thick wall of water, or polyethylene, stops most of the stellar wind. Galactic cosmic rays pass through meters of metal. They pass through the hull of any spacecraft anyone knows how to build. They pass through the human body and deposit their energy as they go, ionizing the atoms they encounter, severing chemical bonds and fracturing strands of DNA with a directness that lower energy radiation cannot achieve. The heavy nuclei among them deserve particular attention because they are a small fraction of the flux and a large fraction of the damage. The energy a charged particle deposits scales roughly with the square of its charge. An iron nucleus carries 26 units of charge, which means it deposits energy at something like 670 times the rate a lone proton does. A single iron nucleus crossing a cell does not knock out one chemical bond. It leaves a track of destruction through everything along its path, and the cells on either side of that track show damage too. This is qualitatively different from anything encountered in terrestrial radiology, which is one reason the medical models built from decades of terrestrial exposure data are of limited use here. We are extrapolating from the wrong kind of injury. The numbers are worth stating plainly. Aboard a spacecraft outside the Earth's magnetic field, a crew member absorbs roughly 1 millisievert per day from galactic cosmic rays alone. That is approximately the dose of a full-body medical scan, absorbed every day, without interruption, for as long as the mission lasts. Astronauts on the orbital station, which sits inside the partial protection of the Earth's magnetic field, already absorb roughly 10 times the annual dose of someone standing on the ground. A 6-month transit to a neighboring planet, which leaves that protection behind entirely, is estimated to approach or exceed the career limits that space agencies set for radiation workers. 6 months. To a neighboring planet. It helps to know the scale those doses are measured against. The sievert is a unit of biologically weighted dose, and the landmarks along it are grim and simple. Roughly 1 sievert absorbed quickly produces radiation sickness. 5 is fatal to about half of the people who receive it. 8 to 10 is uniformly fatal. A millisievert a day, sustained, reaches 1 sievert in under 3 years, and 5 in something over 13. There is also a genuinely awkward interaction with the sun's own cycle. Solar magnetic activity partly screens the inner solar system from galactic cosmic rays, so the flux falls when the sun is most active and rises when it is quiet. Which produces the unhelpful result that the safest years to travel with respect to cosmic rays are the most dangerous years with respect to solar storms, and the reverse. There is no window that is good for both. Now apply that to the crossing. A crude voyage to the nearest star at 1% of light speed takes something over 400 years. Even an implausibly fast crossing at 1/10 of light speed takes 40 to 50. Across those durations, without shielding that does not currently exist in any form, the cumulative galactic cosmic ray dose is not an elevation of statistical risk. It is fatal, many times over, as a certainty. The arithmetic does not require careful modeling. It requires only multiplication. And here the episode reaches the clearest single illustration of what makes this problem different from an ordinary hard problem. Shielding works, up to a point, and then it begins to work against itself. Passive shielding is straightforward in concept. Put mass between the crew and the incoming particles. Water is effective, and it has the enormous practical advantage that the ship must carry water regardless. Hydrogen-rich polymers are better than metal per unit mass, because hydrogen nuclei absorb energy without fragmenting into anything worse. Polyethylene shields roughly 20% better than aluminium for the same weight, for exactly that reason. But at the highest energies, thickness turns treacherous. When a high-energy primary particle strikes a shield, it does not simply stop. It shatters the nuclei it hits and produces a cascade of secondary particles, including neutrons, which are themselves deeply penetrating and biologically damaging. At moderate shield thickness, that secondary shower can deliver a higher dose to the crew than the unshielded flux would have delivered. The dose curve falls at first, then rises through a genuinely bad middle region, and only falls again at thicknesses far beyond anything a ship could carry. Aluminium, the traditional structural material of spacecraft, is among the worst offenders for producing those secondaries. What that means in practice is that a partly shielded ship can be more dangerous than an unshielded one, and the shield that genuinely works is measured in meters of water. Hundreds of tons of it, wrapped around the living space. Which returns the entire problem to the previous part, where mass is precisely the thing that cannot be afforded. There is a more elegant answer, and it has been studied seriously. Generate a magnetic field around the ship and deflect the charged particles before they arrive, the way the Earth does. The physics is sound. The difficulty is that the field strengths required to turn a multi-giga-electron-volt ion nucleus are enormous. The superconducting coils that would generate them are heavy. They must be kept extremely cold. They consume continuous power. and the field exerts forces on its own structure that have to be resisted mechanically. Nobody has built one. It remains the most plausible long-term answer to the problem, and it is entirely unproven. There is one detail about all of this that is worth sitting with, because it turns an abstraction into something a person can feel. A significant fraction of astronauts on long-duration missions report seeing flashes of light with their eyes closed, in complete darkness. Brief streaks, points, occasionally a diffuse cloud. These are individual charged particles passing through the retina and the visual system and being perceived as light. The body registers the damage as illumination. It is one of the strangest facts in the whole subject, and it is entirely routine. Beyond cancer risk, which is the most studied consequence and the easiest to model, exposure at deep space doses affects the central nervous system in ways researchers are still working to characterize. Animal studies at comparable exposures show persistent changes in the structure of neurons and measurable deficits in learning and memory. Imaging of astronauts after long missions shows structural changes in the brain, shifts in white matter, redistribution of cerebrospinal fluid, and an upward displacement of the brain within the skull. The mechanisms are not fully understood. The doses studied are far below what an interstellar crossing would deliver, and there is no particular reason to expect the effects to level off. Part 6. The storms and the weather a ship makes for itself. The third member of the radiation family is the least predictable, and in some ways the most immediate. Occasionally, the sun releases an enormous burst of high-energy protons over the course of hours, driven by a flare or by the shock front running ahead of a coronal mass ejection. On Earth, these events produce geomagnetic storms, disturb satellites, interfere with radio, and occasionally stress power grids. In deep space, aboard a thin-walled vessel with no magnetic protection, a major event delivers a radiation dose that can reach dangerous or lethal levels within hours. There is a well-documented near miss in the record. One of the largest such events ever measured occurred in the gap between two crewed lunar missions. Had it arrived while a crew was in transit, or standing on the lunar surface with only a suit between them and it, the exposure would have been severe and quite possibly fatal. Nothing prevented it from arriving a few months earlier or a few months later. The timing was luck. Purely statistical, entirely unearned, and complete. That matters for a long crossing in a specific way. Over a journey of decades or centuries, the probability of encountering multiple major particle events approaches certainty. Not likelihood, certainty. Each one is a window of acute vulnerability, and each one arrives with warning measured in minutes to a couple of hours at the very best, because the light and the fastest particles arrive together and the bulk of the dose follows close behind. There is no forecasting service that would help. There is only the alarm, and however long it takes to reach shelter. The historical record suggests the modern era has been mild. Solar events, energetic enough to be detected by instruments at the Earth's surface through the entire thickness of the atmosphere, occur only a handful of times per solar cycle, and it is that class of event that would be dangerous in deep space. But records preserved in ice cores and in the growth rings of very old trees show at least one event within the last several thousand years, perhaps an order of magnitude stronger than anything measured since instruments existed. Nobody was watching when it happened. It simply left a mark in the wood and the ice, and waited to be found. A ship departing on a voyage of centuries would be sampling that distribution, not the comfortable recent portion of it. The shelter is the standard answer, and it does work. A small, heavily shielded compartment that the crew retreats into for the duration of an event. Solar particles are relatively easy to stop, and the events are short, so a few tons of well-placed water and stored waste around a single small volume is genuinely effective. But it imposes a real architectural constraint. The shelter must be reachable from anywhere aboard within minutes, which puts a hard ceiling on how spread out the vessel can be. A large ship is a slow ship to run across, and a ship designed around a storm shelter is a compact ship, whether or not compactness suits anything else about it. And the shelter does nothing whatsoever for the other problem. Galactic cosmic rays arrive continuously, from every direction, for the entire voyage. There is no event to retreat from. There is no all clear. There is only the steady accumulation, every hour, for as long as the crossing lasts, which is the difference between weather and climate. There is also the matter of the sun's protection fading behind you. The heliosphere, the bubble the solar wind inflates against the interstellar medium, screens out a meaningful fraction of the lower energy galactic cosmic rays. A ship crosses the outer boundary of that bubble somewhere beyond 100 times the Earth-to-Sun distance, which on any realistic voyage happens within the first couple of decades. After that, for the remaining 99% of the journey, the screening is gone. Leaving home means leaving the last piece of shelter the sun provides, and doing it very early in the trip. But the most interesting hazard is the one the ship creates for itself, and it is the cleanest demonstration of why this problem is not a list of obstacles to be worked through one at a time. At walking pace, 1 hydrogen atom per cubic centimeter is nothing. It is so close to nothing that no instrument in ordinary use would register it. At half the speed of light, each of those atoms arrives at the hull carrying the kinetic energy of a cosmic ray. The ship is not traveling through a near vacuum. It is traveling through a continuous, forward-directed radiation field that its own velocity is generating, moment by moment, from material that was entirely harmless before the ship arrived. The arithmetic is worth following. A proton arriving at a stationary target at 50% of light speed carries roughly 100 mega-electron-volts of energy, which is squarely in the range that penetrates ordinary hull material. The number of particles arriving per second scales with velocity, and the energy each one carries scales faster still. So the faster the ship travels in order to shorten its exposure time, the more intense the environment it generates around itself. There is a crossover point, beyond which going faster increases the total dose, rather than reducing it. And that crossover sits uncomfortably close to the velocities that would make the journey worth attempting in the first place. The dust is worse than the gas. An interstellar dust grain a fraction of a micrometer across, arriving at 20% of light speed, carries kinetic energy comparable to a rifle round concentrated into a point smaller than a bacterium. It does not dent the hull. It vaporizes a crater and sends a shock wave through the surrounding structure. Larger grains, still microscopic by any ordinary standard, would punch straight through. And over 4 light-years, a ship sweeps out an enormous volume of space, which turns the encounter from a possibility into a schedule. You do not ask whether it happens. You calculate how often. There are partial answers, and each one arrives with the same bill attached. A sacrificial leading-edge shield mounted ahead of the vessel absorbs the impacts, at the cost of mass, and it must be held some distance out in front, so that the debris plume from each strike has room to spread before reaching the hull. That means a long, fragile boom under continuous bombardment for the entire voyage. A cloud of dust deliberately released ahead of the ship to break up incoming grains has been proposed, at the cost of complexity. A magnetic or electrostatic deflector might turn charged particles, but most dust grains carry very little charge. Every one of these adds mass or power. Both of those feed directly back into the fuel problem, which was already the thing that could not be solved. There is one small consolation in the geometry. At relativistic speeds, the incoming flux is beamed forward by aberration, so almost all of it arrives at the front of the vessel, rather than from every direction at once. That makes the shielding problem simpler in shape than the cosmic ray problem, if not in scale. You know where it is coming from. You just cannot afford what it would take to stop it. It is worth pausing here to count what has accumulated, because the episode is about to turn inward, and the walls behind us should be visible from where we are standing. There is the distance, which outlasts the entire written record of our species at the fastest speed we have ever reached. There is the medium, which offers no return, no resupply, and no conversation that is less than 8 years old. There is the engine, which nobody knows how to build, and whose one credible design was abandoned for reasons having nothing to do with physics. There is the arithmetic, which demands more propellant than there are atoms in the universe, and which softens only when handed a substance we have made 15 billionths of a gram of. And there is the radiation, which arrives from everywhere at once, and cannot be shielded without adding exactly the mass that makes the fuel problem worse. 5 walls, and not one of them has yet involved a human being. Every difficulty so far belongs to the ship. That is where the accounting changes, because the thing the ship is carrying has requirements of its own, and they turn out to be no easier to meet. None of this, it is worth saying, is aimed at anyone. The particles are not directed. The dust is not waiting. The sun does not release its storms on any schedule that has anything to do with us. The universe is not hostile to the crossing. It is simply arranged in a way that has no particular use for a warm, soft, slow-moving thing that needs to keep its water on the inside of its skin. Part 7. The body forgets the ground. The human body was not built for stillness. It was assembled for a planet. For gravity pulling constantly downward, for the daily work of standing and moving and resisting collapse, for a rhythm of light and dark that tells an internal clock when to sleep and when to wake. Every system in the body assumes there is a world underneath it. Remove the world, and the body begins, slowly and then less slowly, to disassemble the parts it no longer appears to need. This is not speculation. It is among the most thoroughly documented phenomena in all of space medicine, accumulated across decades of continuous human presence in orbit and, before that, aboard earlier stations. Crew members who spend 6 months in weightlessness come back changed. Not subtly. Measurably, in ways that require months of rehabilitation to partly reverse, and in some cases, in ways that do not fully reverse at all. Bone goes first, and it goes fastest. In the absence of gravitational load, the skeleton begins to shed density. The body, in its efficient way, stops investing resources in structures that no longer appear to be carrying anything. Bone mineral density falls at roughly 1 to 2% per month in the regions most affected, which are the lumbar spine, the hip, the neck of the femur, and the heel. Those are exactly the load-bearing regions, which is the point. The skeleton is not decaying at random. It is being selectively withdrawn from the places that are no longer being asked to work. The comparison that makes this land is with aging on the ground. Age-related bone loss on Earth runs at roughly 1 to 2% per year in the years following menopause, and it is considered a serious clinical condition requiring treatment. In orbit, the same loss occurs about 12 times faster in otherwise healthy adults in the prime of their lives. The mineral does not vanish. It is resorbed into the bloodstream and excreted, which sharply raises the concentration of calcium in the urine and with it the risk of kidney stones. That condition is unpleasant on Earth and a genuine emergency aboard a vehicle with no surgical capability and no way home. It is one of a long list of ordinary terrestrial problems that change character entirely once nobody can be evacuated. The recovery is also incomplete, which is the part that matters most for a long crossing. After 6-month missions, bone density recovers substantially across the following 1 to 2 years back on the ground. But studies of returning crews show that some regions, particularly the hip, do not return to their pre-flight values even after several years. And the bulk density figure conceals something worse. Bone is not solid. Its strength comes from an internal lattice, a microscopic architecture of struts and plates, and that architecture recovers more slowly and less completely than the density number suggests. A crew member can produce a normal-looking scan and still have a structurally weaker skeleton than the one they left with. Now scale it. After a year, the losses are considerably more severe than after 6 months. After a decade, which is the duration of even the most optimistic near-term interstellar proposals and a small fraction of any realistic one, the losses are, by any current understanding of human physiology, incompatible with the ability to stand and walk under a planet's gravity, which produces the quietest and most complete failure in the whole subject. A crew arriving at another star after decades of weightlessness would arrive, if they arrived at all, unable to use the ground they crossed the void to reach. Muscle follows the same logic and the same schedule. Without the constant low-level work of resisting gravity, muscle mass declines steadily, and it declines fastest in precisely the muscles a planet requires. The calves, the quadriceps, the muscles of the back and trunk that hold a body upright without conscious effort. Losses on the order of 20% in the postural muscles within the first weeks are typical when no countermeasures are applied. The fiber composition shifts too. Slow, fatigue-resistant fibers convert toward faster ones that tire more easily, so the muscle that remains is not only smaller, but the wrong kind for standing around on a planet all day. The heart is a muscle, and it is subject to the same accounting. It is designed to pump blood upward against gravity's pull. In weightlessness, it finds that the fluid redistributes toward the head with no effort required at all, so it compensates by working less. Over time, it remodels. Measurements of long-duration crews have recorded reductions in cardiac mass on the order of 1/5 after a year in orbit, along with a shift toward a more spherical shape as the chamber walls adapt to the reduced demand. A smaller, rounder, weaker heart returning to gravity struggles to meet a demand that has been restored all at once. Near fainting on standing is common after long missions, and crews are routinely carried from the capsule rather than walking out of it. The heart has, in a real and measurable sense, forgotten what a planet asks of it. Blood itself changes. Within days of arriving in weightlessness, the body reads the fluid shift toward the chest as an excess of volume and reduces plasma accordingly, then reduces red cell mass to match. The result has an informal name among researchers, and for a long time it was assumed to be a brief adjustment that settled once the new equilibrium was reached. More recent work suggests otherwise. The destruction of red blood cells appears to run elevated for the entire duration of a flight, rather than settling after the first weeks, and it remains elevated for a year after return to the ground. Nobody knows what a permanently elevated rate of red cell destruction does across decades, because nobody has ever been in that state long enough to find out. That sentence, in various forms, is the honest answer to most questions in this field. There are smaller changes that arrive faster and are stranger to sit with. Within days of reaching orbit, crew members grow taller by several centimeters because the discs between the vertebrae are no longer being compressed by the weight of the body above them. The spine simply lengthens. It is accompanied by back pain, which is among the most common early complaints, and it reverses on return with more discomfort than it caused going up. Tendons and cartilage adapt to the reduced stress in ways that make the return to gravity a period of elevated injury risk. Grip strength falls. Balance degrades badly enough that returning crews need assistance walking for hours to days after landing and require weeks of careful work to move normally again. On arrival at another star, that period of helplessness would come with no support crew waiting, no medical team, and no gravity to practice in, except whatever the new world happened to have. Fine motor control shifts as well, in a way that is easy to overlook. The absence of a consistent downward direction alters proprioception, the body's sense of where its own limbs are, and tasks requiring precise application of force have to be relearned. Wound healing also appears to be impaired in weightlessness, which for a crew with no surgical backup compounds every other risk on the list. And the total sample of human beings who have spent more than a year continuously in these conditions is fewer than 10 people. The longest single flight on record runs a little over 14 months. The longest career total, accumulated across several missions with long recoveries in between, is a little over 2.5 years. Every conclusion about long-duration exposure rests on a data set smaller than a modest clinical trial, and the crossing would require extrapolating it by a factor of 30 or more. Exercise helps, and it is worth being clear that it helps a great deal. Vigorous, mandatory daily exercise, using resistive devices that simulate weight-bearing loads along with treadmills and cycling machines, substantially offsets these losses. Crews now return with far better preserved bone and muscle than the early long-duration crews did, and the improvement is one of the genuine success stories of the field. It is not a small achievement. It is the difference between coming home damaged and coming home impaired. But the offset is partial, and it is expensive. It reduces the losses. It does not eliminate them. And the cost is 2 to 3 hours of every single day, sustained across years or decades of a crossing, which is a significant fraction of every crew member's waking time and a significant fraction of their caloric budget as well. Every calorie burned on a treadmill is a calorie that had to be carried from Earth or grown aboard in a closed system with no margin. Every hour on the resistive device is an hour not spent on the 1,000 other tasks a long-duration crew must perform, and the crew is small because mass is expensive. The equipment itself must survive decades of daily heavy use, with bearings and cables and actuators replaced from a stock of spares that was fixed at departure. On a 40-year voyage, the exercise machine is not a convenience. It is a life support system, and it wears out. The arithmetic of prevention, in other words, is nearly as demanding as the damage it prevents. That is a pattern by now, and it will hold for the rest of the ledger. Part 8. The eyes and the quiet failures. Some of what the crossing does to a body announces itself. Bone loss shows on a scan. Muscle loss shows in a photograph. But the failures that matter most on a long voyage are the ones that arrive without any announcement at all, and the clearest of them begins with something as ordinary as where the blood goes. In weightlessness, bodily fluids migrate toward the upper body. The chest, the neck, and the head. Crew members describe the sensation as similar to hanging upside down, continuously, and it does not go away. The face puffs. The sinuses congest, which dulls both taste and smell, to the point where food aboard is prepared far more strongly flavored than it would be on the ground. The legs become noticeably thinner within days as the fluid drains upward out of them, an effect visible in photographs and familiar enough to crews that it has acquired an informal name. What that fluid does inside the skull is the problem. Pressure within the head rises, mildly but persistently, and that sustained elevation has consequences for the most delicate structures the body contains. There is a condition, identified and named only within the last 15 years as longer missions became routine, that affects a substantial fraction of crew on long flights. It went unrecognized for decades of spaceflight, partly because the missions were short and partly because nobody thought to look at the eye as an organ under pressure. The mechanism is now reasonably well described. Elevated pressure flattens the back of the eyeball, produces visible folds in the layers of the retina, swells the head of the optic nerve where it enters the eye, and alters the shape of the whole optical system. The practical result is a shift in refraction. Most affected crew become more farsighted, sometimes by enough that their corrective lenses have to be changed partway through a mission, and spare glasses in a range of prescriptions are now carried as standard equipment. In a sample of crew who had spent significant time aboard the orbital station, more than half showed some degree of these changes. The part that matters for a crossing is that some of it does not resolve. Not temporary blurring during the flight, corrected on return. Structural change to the eye that persists years afterwards, with permanent degradation of visual acuity in some of those affected. The condition is not fully understood. No reliable countermeasure exists. Devices that apply gentle negative pressure to the lower body, drawing fluid back down toward the legs, are being trialed, and the early results are encouraging and preliminary. And every observation in the whole literature comes from exposures measured in months against a crossing measured in decades. That is worse than it sounds, and it is worth taking a moment over why. A crew several decades into a voyage would be navigating, reading instruments, performing repairs on machinery with fine tolerances, and if it came to it, performing surgery with eyes that had been slowly and irreversibly altered by the journey itself. Of all the ways the crossing degrades a crew, this is the one that most directly degrades their capacity to manage every other problem on the list. It is not the most dangerous item by itself. It is the one that undermines the response to all the others. There is also reason to think it compounds. Some researchers suspect the vision changes are worsened by cumulative radiation exposure to the optic structures, which would mean the interstellar case is not a simple extension of the orbital case, but a considerably worse one. Two slow processes acting on the same tissue over a duration neither has been studied across. Immunity is the next quiet failure. In weightlessness, immune function shifts and, in the ways that matter most, is suppressed. Cell-mediated immunity weakens. The balance of signaling molecules moves toward a mildly inflammatory state that persists. And latent viruses, the ones most adults carry silently for their entire lives, begin to reactivate. The herpes family in particular, including the viruses responsible for cold sores and for chickenpox, are shed at rates several times higher in crew than in matched groups on the ground, frequently with no visible symptoms whatsoever. The body's surveillance systems, like its skeletal systems, appear to down-regulate in the absence of the stresses they evolved to manage. The compounding problem is what that means in a sealed environment. A crew far beyond any possibility of medical resupply, with suppressed immunity and reactivating latent infection, breathing air that circulates through the same filters and touching the same surfaces, is a medical environment of real fragility. Any pathogen that begins circulating reaches everyone. There is also evidence that some bacteria become more virulent and more resistant to antibiotics under spaceflight conditions, at the same time as the immune system defending against them is doing less. Both curves move the wrong way at once. The population of microbes a person carries changes too. The composition of the gut microbiome shifts measurably across a long mission and does not fully return to its previous state afterwards. On the ground that is a curiosity. Across decades in a closed system, where the only microbial exchange available is with the same few dozen people and the same recycled surfaces, the consequences are entirely unknown, and the microbial ecology of a ship a century into its voyage would be something nobody has ever studied. Hearing loss has also been documented on long missions, attributed in part to continuous mechanical noise from pumps and fans, which aboard a vessel with a running drive would be a permanent feature of the environment rather than an intermittent one. There is no quiet place on a ship that has to keep its own air moving. Medicine itself does not keep. Pharmaceuticals degrade, with shelf lives typically measured in a few years, and radiation exposure accelerates the breakdown of many compounds well beyond their terrestrial rates. A crossing of decades cannot simply carry its own pharmacy. It would have to synthesize medicines along the way, which means carrying the feedstocks, the equipment, the reference standards, and the expertise to manufacture and validate drugs inside a closed system. That capability does not currently exist anywhere, at any scale, even on the ground with an entire industrial base to draw on. Surgery is possible in weightlessness, in principle, and has never been performed on a human being. Blood does not pool. It forms domes on the surface of a wound and then drifts free in the air. The surgical field has to be enclosed to contain it. Instruments float away if released. And the people performing the operation would be the same small group who are themselves immunosuppressed, radiation exposed, and visually degraded, with no possibility of consulting anyone whose advice would be less than 8 years old. Dental care sits on the same list and gets far less attention than it deserves. An abscessed tooth is trivially treatable on Earth and potentially fatal in a vehicle with no dentist, no antibiotics that have not expired, and no evacuation. Sleep is its own slow difficulty. Without a planet's day, the internal clock has nothing to set itself by. Orbital crews see 16 sunrises in 24 hours and rely on scheduled lighting to hold a rhythm. Even so, sleep quality is persistently poor. Actual sleep duration falls short of what is scheduled, and the use of sleep medication among orbital crews is widespread. On an interstellar crossing, there would be no external cue at all, ever. Every rhythm the crew lived by would be manufactured, maintained by machinery, for an entire lifetime, with the quality of everyone's rest depending on a lighting system continuing to work. And then there is the question the whole thing eventually arrives at, which is children. Any crossing longer than a few decades requires that people be born and raised aboard. Almost nothing is known about this. Human conception, gestation, and development have never once occurred outside a planet's gravity. Animal studies suggest reduced gravity affects skeletal development and, more troublingly, the formation of the vestibular system, the apparatus of balance in the inner ear, which develops in response to a consistent gravitational direction that simply would not exist. A child born and raised in weightlessness would not be a smaller version of a person from Earth. They would be an organism shaped by a different environment, almost certainly unable to stand on the surface of the world their ancestors set out for, and entirely healthy by the only standard they had ever known. Every one of these changes, it is worth noticing, is the body doing exactly what it evolved to do. Economizing. Adapting. Letting go of what is no longer being asked of it. The failure is not the body's. It is the mismatch between what the body optimizes for and where the ship is going. Part 9. The spin that was supposed to fix it. There is an obvious answer to everything in the last 2 parts, and it has been the obvious answer for 100 years. If the body needs gravity, give it gravity. Rotate the habitat, and everything inside it is pushed outward against the rim, which then works as a floor. This is not exotic physics. It is the same effect that keeps water in a bucket swung on a rope, applied at a larger scale and a slower pace. Nothing about it is speculative. It has simply never been done with a crewed spacecraft, which is a different kind of statement, and the reason it has never been done is instructive. The whole design rests on a single trade. The apparent gravity produced depends on the radius of the rotating habitat and on the square of its rotation rate. A small ring has to spin fast to produce useful gravity. A large ring can spin slowly. That is the entire tension, and it is unforgiving from both directions. Here are the numbers that matter. To produce a full Earth gravity at 2 revolutions per minute, which is the rate widely regarded as comfortable for most people without extended adaptation, the radius has to be roughly 224 meters. That is a rotating structure nearly half a kilometer across, assembled in orbit because nothing that size can be launched in one piece, held rigid against its own spin, and then carried across 4 light-years. Accept 4 revolutions per minute instead, and the radius drops to around 56 meters, which is far more buildable and considerably less pleasant to live in. Accept a lower gravity, say 1/3 of Earth's, and the radius drops again, at the cost of reintroducing exactly the problem the spin was meant to solve. Fast rotation is a problem, for reasons that are worth understanding, because they are not obvious. In a rotating frame, any movement that is not purely along the axis of rotation produces a sideways force. Reach upward and your arm is deflected. Climb a ladder toward the center, and you drift to one side. Set an object down, and it does not stay quite where you left it. None of this is dangerous, and all of it is constant. The serious effect is in the inner ear. Turn your head in a rotating environment, and the fluid in the vestibular system is dragged across the rotation, producing a strong sensation of tumbling that has no visual correlate whatsoever. Your eyes report a stable environment. Your inner ear reports that the world is rolling over. That mismatch is the same mismatch that produces motion sickness, and in a rotating habitat, it is triggered by the simple act of looking around. It is the practical limit on rotation rate, and it produces nausea in most people above a few revolutions per minute until they adapt. Adaptation takes several days. It is genuine and measurable in ground-based rotating rooms, and it does not take in everyone. It also has to be undone on leaving, and the transitions in both directions are the worst part of the experience. There is a subtler oddity in any habitat small enough to build, which is that gravity varies with height. In a 56-meter ring, a standing adult's head experiences roughly 3% less apparent gravity than their feet, which is tolerable and probably not noticeable after a while. Halve the radius, and the difference becomes pronounced enough to feel on standing up and sitting down. Direction matters too. Walking with the rotation makes you effectively heavier. Walking against it makes you lighter. A dropped object does not fall straight down, but curves as it falls. None of this is harmful. All of it means that every physical intuition a crew member holds has to be rebuilt, and that any child raised aboard would build a complete set of intuitions useless anywhere else in the universe. Then there is the structural bill, which is where the whole idea meets the fuel problem. A rotating habitat is a pressure vessel being pulled apart by its own spin, continuously for the entire voyage, with no opportunity for inspection by anyone outside. It needs a counter-rotating element, or a second ring turning the other way, so that the ship as a whole carries no net angular momentum. Otherwise, every attempt to turn the vessel is a fight against a gyroscope the size of a building, and docking, thrusting, and pointing all become substantially harder than they already are. Spinning up and spinning down cost propellant or reaction wheel capacity, so a rotating ship cannot casually stop turning in order to perform a maneuver. Any leak, any impact, any asymmetric movement of mass inside produces a wobble that has to be actively damped for the life of the mission. And the rotating structure provides no protection whatsoever from radiation, which means the shielding mass and the structural mass are additive rather than shared. All of that mass feeds directly back into the arithmetic that could not be satisfied in the first place. The interior systems inherit the strangeness as well. Fluid behavior in a rotating frame is subtly wrong in ways that affect plumbing, cooling, and agriculture. Water does not fall quite straight. Drains work, but not exactly as designed. Any system relying on gravity feed has to be laid out with the rotation in mind, and any system that crosses between the rotating section and the stationary hub has to handle the transition. Which brings up the transfer points themselves. Moving between the spinning part of a ship and the still part of it means passing through a region where apparent gravity falls away to nothing across a short distance while the vestibular system tries to keep up. Those junctions are reliably the least pleasant places aboard any rotating design, and they cannot be avoided because the drive, the sensors, and the docking hardware all have to live on the non-rotating part. There are lighter approaches. A tether and counterweight architecture in which two masses spin about a common center on the end of a long cable achieves a large effective radius for a small fraction of the structural mass of a rigid ring, and it is by some distance the most plausible near-term way to do this. It has been proposed repeatedly. It has never been flown with people aboard. But the deepest problem in this part is not engineering at all. It is that nobody knows what to aim for. Human physiology has been measured at exactly 2 gravity levels. 1, on the surface of the Earth, in enormous detail across all of medical history. And effectively 0, in orbit, in considerable detail across several decades. There is no data at 1/3 of a gravity, or 1/2, or 2/3. Nobody knows whether 1/3 of a gravity preserves bone. Nobody knows whether the body's response is linear with the load, or whether there is a threshold below which it gives up entirely, regardless of how close to the threshold you sit. Every partial gravity habitat design in existence is a line drawn between 2 points. And a line through 2 points can be drawn to support almost any conclusion you would like it to support. That gap in the data is not incidental. It means the central design parameter of any rotating starship, the number that determines its radius and therefore its mass, and therefore whether it can be built at all, is currently a guess. The experiment that would settle it, a rotating facility in orbit holding people at partial gravity for months at a time, has been proposed for half a century and has never been funded. The alternatives to spin are thinner than they look. Short radius centrifuges, essentially a spinning bed a crew member lies on for an hour a day, have been studied as a countermeasure, and the evidence suggests intermittent loading helps meaningfully but does not substitute for continuous weight. Suspended animation or induced torpor is often offered as the answer to everything in this part of the story. It is genuinely promising in early animal work. It has never been achieved in a human being for longer than short, carefully monitored, medically induced periods. And it would not by itself address bone loss, which continues in an unloaded body whether that body is conscious or not, nor radiation, which does not care whether anyone is awake, nor the plain fact that somebody has to be conscious to repair the ship. So the spin is a real solution to a real problem, and it arrives with its own invoice attached. That is now the third time this has happened, and it will not be the last. Part 10. Time, and the gift behind a locked door. There is one place in the physics of interstellar travel where the universe appears, briefly, to offer something. A concession. A loosening of the constraints that have tightened around every other approach. It arrives inside the theory of special relativity, in a phenomenon called time dilation, and held at a certain angle, it looks almost like a solution. The idea is this: time does not pass at the same rate for all observers. A clock in motion runs slow relative to a clock at rest. Not as a malfunction of the clock, not as an illusion produced by the difficulty of measuring things that are moving, but as a genuine feature of the geometry of space and time. The faster something moves, the more slowly time passes aboard it, relative to everything it has left behind. At ordinary speeds, the effect is immeasurably small. At half the speed of light, time aboard the ship passes at about 87% of the rate it passes at home. At 90% of light speed, roughly 44%. At 99%, about 14%. At 99.9%, it falls to around 4.5%. The closer the ship approaches light speed, the more severely its own time compresses relative to the world it departed from. What that would mean for the crossing is genuinely remarkable. At sufficiently high velocity, a ship could cross 4 light years, while only months or a few years passed for the people aboard, even as rather more than 4 years passed at home. And the effect compounds with distance rather than washing out. A voyage of thousands of light years, under continuous acceleration at a comfortable 1 gravity, would take a few decades of shipboard time. The whole galaxy becomes, in principle, crossable inside a single human life. There is a way of seeing the same thing from the other side, which some people find clearer. From the ship's frame of reference, the distance itself contracts. The crew do not experience a fast crossing of a long distance. They experience an ordinary crossing of a short one. The 4 light years shorten along the direction of travel, and the ship simply covers the shortened gap at its own steady pace. Both descriptions are correct. They are the same fact, seen from 2 positions. This is real physics, and it is not a theoretical curiosity. It has been measured directly and repeatedly. Atomic clocks carried aboard aircraft and flown on satellites run at measurably different rates from identical clocks left on the ground, precisely as predicted. Unstable particles created high in the atmosphere survive long enough to reach the surface only because their internal clocks run slow at the speeds they travel, and without that effect, they would decay far above our heads. The satellite navigation system in every phone corrects for the effect continuously and would accumulate positional errors of kilometers per day if it did not. This is not a proposal. It is engineering practice. And the acceleration that would produce it would fix almost everything in the previous 3 parts at a stroke. A ship under continuous 1 gravity acceleration has a floor that behaves exactly as a floor should. No spin. No Coriolis forces. No vestibular confusion. No bone loss, no fluid shift, no cardiac remodeling, no eye pressure. It would reach relativistic speed in about a year of steady push and cross to the nearest star in something under 6 years of shipboard time. It solves the propulsion problem and the biology problem in the same motion. So for a moment it seems as though the crossing might be survivable after all. And then the other side of the concession arrives. The kinetic energy required does not rise in proportion to velocity. It rises without limit as light speed is approached, because the very same equations that slow the clock also make the ship progressively harder to accelerate. Every increment of speed costs more than the increment before it, and the cost climbs toward infinity as the ship nears the boundary. The rocket equation, which already produced absurd mass ratios at 1% of light speed, becomes so far beyond absurd at 99% that the numbers stop functioning as numbers. They become symbols, standing in for quantities that have no physical referent anywhere. The concrete version is this. Accelerating a crude vessel to 99% of light speed and then stopping it again at the far end, by any known or theorized method, requires energy exceeding by an enormous margin the total output of the Sun across a span far longer than any civilization has existed. Continuous one-gravity acceleration for a year means a sustained power output that no conceivable engine produces, and it has to be produced without carrying the reaction mass that would be needed to produce it. The gift is real. The price is not payable in any currency that exists. And the faster ship is also the more exposed ship. Everything from the sixth part applies with increasing force. At the velocities where time dilation becomes generous, the interstellar medium is a forward-directed particle beam of extraordinary energy, and the residual warmth of the early universe itself shifts upward into something that contributes to the dose. The gift and the injury arrive together, from the same source, for exactly the same reason. The thing that compresses the journey is the thing that irradiates it. There is also a quiet asymmetry in the gift that is easy to miss. Time dilation is one-directional in its consequences for anyone who returns. A traveler who goes out at relativistic speed and comes back arrives younger than the people who stayed, which means every relativistic voyage is a one-way trip in time, even when it is a round trip in space. The crew would come home to a world that had moved on without them, to institutions they no longer recognized, to families a generation or two further along. There is no version of the journey that returns anyone to the place they left. And the sky itself would look nothing like a starfield sliding past. At relativistic velocity, aberration gathers the light of the entire sky forward into a bright, blue shifted circle directly ahead, while everything behind darkens and reddens toward invisibility. The stars do not stream by on either side. They crowd into a single brilliant point of destination, and the rest of the universe closes behind like a door. This is the structure of the crossing at its most fundamental, and it is worth stating in full because it is the whole argument of this episode in a single shape. Every approach that partially solves one problem makes another problem worse. Time dilation compresses the journey subjectively, but requires velocities that make the fuel problem infinite and the radiation problem lethal. Shielding reduces radiation, but adds mass that makes the fuel problem worse. Spin restores gravity, but adds mass and structural fragility and does nothing about radiation. Slower speeds ease the fuel problem and reduce the self-made radiation, but eliminate time dilation entirely and stretch the journey into centuries, which hands the whole thing to a different problem again. The constraints do not line up in a row waiting to be worked through. They pull in opposite directions, and every movement toward one solution is a movement away from another. Physicists sometimes describe this cluster as a region of constraint space, where the requirements of a successful mission cannot all be satisfied at once. That is a careful way of saying something quite stark. It is not that we lack the technology to thread the needle. It is that the eye of the needle narrows as you approach it. The shortcuts deserve an honest word before this part settles. Warp geometries and traversable wormholes do appear as valid solutions in the equations of general relativity. That is a real fact, and it is not nothing. But appearing as a mathematical solution and existing as a physical object are entirely different categories of thing. Every one of those solutions requires matter with negative energy density, a substance never observed in any quantity that would matter, whose existence in bulk appears to be forbidden by other well-tested results. The only known effects producing negative energy density are minute quantum phenomena between closely spaced plates, and there is no known route from that to the macroscopic quantities the geometries demand. No wormhole has ever been detected. Some of the warp proposals have had their energy requirements reduced enormously by later reformulations, from more than the mass energy of the observable universe down to something on the order of a planet, which is progress of a kind and still an infinite distance from a roadmap. They are a permission slip, written in mathematics, which the universe has so far shown no sign of intending to honor. It is worth sitting with the strangeness of the offer, rather than only with its withdrawal. The universe contains, inside its own rules, a mechanism that folds enormous distances into a manageable span of lived experience. It did not have to. There is no reason the geometry of space and time had to be arranged so that going fast makes the journey shorter for the traveler. It is almost generous. And it is kept behind a door that those same rules hold firmly shut. Part 11. The society sealed inside the hull. Every problem discussed so far has been a problem of physics, of engineering, or of biology. The distance, the fuel, the radiation, the body's slow forgetting of what gravity requires of it. These are, in a specific sense, clean problems. They have numbers attached. They can be measured, modeled, written on a page and studied. They present themselves fully and then wait to be solved or declared unsolvable, and either answer is an answer. The last problem is not like that. The last problem is a problem of ordinary human time. Not the relativistic time of clocks and velocities, but the plain time of institutions and memory, and the question of what holds a group of people to a purpose that is generations older than anyone alive to carry it. Consider what it would mean to actually attempt the crossing. Not the physics of it, which we have set out at length, but the human architecture underneath it. Someone, somewhere, would have to decide to go. A government, or a coalition of governments, or some institution wealthy and patient enough would have to commit resources across a timeline longer than any institution in human history has ever sustained a single continuous effort. The comparisons that get offered are not as reassuring as they sound. The Great Pyramids were built across roughly 80 years. The largest medieval cathedrals took 2 or 3 centuries in some cases, which is genuinely impressive. But those were built in place, on solid ground, by rotating generations of craftsmen who could walk out each morning and see the structure standing a little higher than it stood the year before. The crossing offers none of that. It is invisible progress through an invisible void, sustained by people who will never see the destination, toward a goal that will not be reached by anyone who remembers why it was chosen. The first generation is the easy one. The crew aboard at departure trained for years. They understand the mission, and they chose it, and they carry its weight willingly, perhaps even joyfully, in the way that first generations of anything carry their purpose as a gift rather than as an inheritance. They are the ones who volunteered. Their children did not volunteer. Their children were born into the crossing. They have never seen Earth except in recordings made before they existed. They have never felt a planet's gravity, only whatever the rotation happens to provide, and to them that is simply what weight is. They know the mission the way anyone knows the circumstances of their own birth, as the given condition of existence, rather than as a decision anyone made. They may honor it. They may resent it. And across the ordinary friction of decades, they will develop their own priorities, their own internal politics, and their own sense of what the ship is for and who it belongs to. By the third generation, the crew is composed entirely of people for whom Earth is a story. The designers of the mission are historical figures. The destination is an abstraction, a star that has been getting incrementally brighter for their entire lives and is still decades away. The people who chose all of this are names on a plaque. So what holds them to it? That is not a question with an engineering answer. It is a question about the tensile strength of human purpose across time, and history, examined honestly, does not offer a great deal of comfort. Institutions fracture. Priorities drift. The meaning that animates a project in its founding generation subsides as the founders fade. No single coherent institutional purpose has ever been sustained across 3 generations without significant transformation of the original intent. Religions come closest, and even they schism, reinterpret, and reform. Nations rewrite their constitutions. Scientific programs are defunded and reoriented. Nothing we have built has held its shape for that long without changing into something its founders would not recognize. There is a documented version of this problem at small scale, and it is remarkably consistent. Across Antarctic overwintering crews, submarine deployments, isolation chamber studies, and orbital missions alike, there is a pattern in which morale drops and interpersonal friction rises during the third quarter of a confined mission. After the novelty is exhausted, and before the end is close enough to feel real. It appears to be a feature of the human response to confinement rather than a product of any particular crew's psychology. Select better people, and it still appears. Train more rigorously, and it still appears. Structure the mission more carefully, and it appears somewhat softened, and still present. Scale that up, and there is no data at all. A crew 20 years into a 40-year crossing, with 20 years still to run, no possibility of return, no communication less than years old, bodies already carrying 2 decades of accumulated change, with 2 more decades of the same waiting ahead. That is the third quarter, at a scale and duration for which no analog exists anywhere in human experience. We do not know what a society becomes after a century of sealed isolation, because we have never observed one. The nearest historical comparisons, island populations and isolated valleys and communities cut off by geography, all eventually re-established contact with the wider world. The ones that did not are recorded as collapses. There is a population problem underneath all of this. A generation ship has to carry a viable gene pool. Estimates for the minimum viable population vary considerably with the assumptions used, but the range most often discussed runs from a few hundred to a few thousand people, with careful management of pairings across generations, and with a founding population large enough to absorb the loss of a substantial fraction to accident or illness without dropping below the floor. Small, isolated populations also face genetic drift and founder effects even above that threshold, which is why serious proposals include stored genetic material to broaden the pool artificially. But notice what that number describes. A few thousand people is not a crew. It is a town. With a school, a hospital, a governance structure, a food system, a waste system, an economy of some kind, and a total mass that returns the entire question to the arithmetic that could not be satisfied in the first place. Every social solution costs mass, and mass was the thing that could not be afforded. A closed society is a strange object in its own right. No immigration and no emigration. No outside culture to refresh its assumptions. No external economy to discipline its priorities. No frontier to absorb its internal tensions, and nowhere for anyone to go who no longer wishes to be part of it. Every conflict that arises has to be resolved inside the same walls that generated it. Every resource dispute, every leadership struggle, every philosophical fracture about the nature and purpose of the voyage. All of it in a space the size of a small town, across decades, with no exit. Language itself would drift, as it always does in isolated communities, so that the people who arrive would not quite speak the language of the people who left. Knowledge is fragile in the same way. The ship must maintain not only its machinery, but the expertise to repair that machinery, taught from one generation to the next, with no external school, no reference beyond what was carried, and no way to consult anyone who built the original systems. Skills decay when the equipment they apply to has not failed in 40 years. The first generation knows how the reactor works because they helped build it. The fourth generation knows how the reactor works because someone told them, who was told by someone else, who was told by someone who was there. The alternatives remove the society problem by removing the society. A sleeper ship, if suspended animation were ever achieved across decades, replaces it with total dependence on machinery, functioning perfectly and unattended for longer than any machine ever has. A seed ship, carrying frozen embryos, removes both the society and most of the life support burden and replaces them with the question of who raises the first generation. In every serious version of that proposal, the answer is machines, which is not obviously a solution to anything. And a crewless probe removes all of it and arrives with nobody aboard, which is where the title has been heading all along. There is one more argument worth naming because it is genuinely awkward. For much of the plausible future, a ship launched later with better technology overtakes one launched earlier and arrives first. Which means the rational departure date is always somewhat after now. Followed strictly, that argument never departs at all. Part 12. What actually fails is the arrival. It is worth laying the whole ledger out in one place, slowly, because the shape of it is the point. There is the distance, which outlasts the entire written record of our species at the fastest speed we have ever reached, and which does not stay put while you cross it. There is the medium, which offers no return, no resupply, and no conversation less than 8 years old. There is the engine, which nobody knows how to build, and whose one genuinely credible design was abandoned for reasons having nothing to do with whether it would have worked. There is the arithmetic, which demands more propellant than there are atoms in the observable universe, and which softens only when handed a substance we have produced 15 billionths of a gram of across our entire history. There is the radiation, which arrives from every direction at once, cannot be shielded without adding exactly the mass that makes the fuel worse, and gets stranger the closer you look at what it does to a nervous system. There are the storms, which arrive on no schedule, and would arrive many times across a long voyage. There is the body, which begins economizing within days, sheds the skeleton it is not being asked to use, remodels the heart down to fit the reduced demand, and does not fully rebuild any of it afterwards. There are the eyes, which change shape under the pressure, and sometimes do not change back. There is the spin, which fixes the body and breaks the mass budget and rests on a design parameter nobody has measured. There is time itself, which offers the single genuine concession in the whole subject, and keeps it behind a door the same physics holds shut. And there is the society, which would have to hold a purpose across more generations than any human institution ever has, sealed inside a hull, with no exit and no outside. Each wall stands behind the last, visible only once the one in front of it has been properly understood. That is why the subject keeps producing optimistic articles. Solve the propulsion and you can write a hopeful piece, right up until you notice the radiation. Solve the radiation and the mass budget collapses. Solve the mass budget with a smaller ship and the society will not fit inside it. But the most important fact about that list is not its length. It is that the items interfere with each other. They are not independent obstacles to be cleared one at a time by a sufficiently determined civilization. They are a set of constraints that pull against one another, and the region where all of them are satisfied at once may simply be empty. That is a different kind of statement about a problem, and it is the honest one. So now answer the question the title asks, plainly. The frightening part of the journey to the next star is not any single item on that list. It is that under nearly every scenario in which the mission technically succeeds, no one who leaves is the one who gets there. Run the arithmetic across the plausible speeds. At 1/10 of the speed of light, which requires propulsion nobody has built and may not be able to build, the crossing takes about 4 decades. A crew departing in the prime of life arrives at the far end of a working career, with bodies that have spent 40 years unlearning how to stand, at a world they would need to be strong to survive. At 1% of light speed, which is still far beyond anything achievable, the crossing takes over 4 centuries. That is 5 or 6 generations. The people who arrive were born inside the crossing, lived their entire lives inside it, and inherited the mission without ever having chosen it. At the speeds we can actually reach today, it is 6,300 years, and there is no meaningful sense in which anybody arrives at all. That is the shape of it. You never arrive. Not because the ship necessarily fails, but because arrival is not a thing that happens to the person who departs. The journey is longer than the traveler. Everything else on the list is detail attached to that one fact. And here is where this should settle, because none of it is a challenge the universe issued. There is no test here. There is no barrier placed deliberately, no puzzle awaiting a sufficiently clever solution, no adversary. It is simply the scale at which the universe operates, and it operated at that scale for billions of years before anything existed that was capable of finding it large. The distance is not aimed at us. It is just the distance. It would be exactly the same if nobody had ever looked up. It also helps to be clear about what kind of impossibility this is, because there are 2 kinds, and they are frequently confused. Nothing described tonight violates a conservation law. Nothing here is forbidden the way perpetual motion is forbidden. Every proposal reviewed across these 2 hours remains physically permitted in principle, and that distinction matters because it means the barrier is energy and time and biology and patience rather than prohibition. There is a column of things the universe will not allow, and a separate column of things it allows but prices beyond any conceivable means. The crossing sits firmly in the second column. Whether that is encouraging or not is a matter of temperament. It is at least accurate. There is one further softening worth holding, which is that a machine can arrive even when a person cannot. A probe has no bones to lose, no eyes to reshape, no third quarter, no grandchildren who never chose any of this. Robotic probes do not answer the question so much as reframe it, and whether a machine reaching the nearest star counts as arrival is a choice about what the mission was for, not a fact about physics. But it is the one version of the crossing that is genuinely on the near side of possible, and it is the version most likely to happen first. There is also a version of the crossing that already succeeds, which is worth saying before the night closes. Information travels the gap easily. The expanding sphere of our own radio emissions has already crossed the nearest star system many times over and continues outward at the only speed the universe permits. 5 spacecraft are drifting out of the Sun's hold right now, aimed at nothing, and they will remain intact and coasting long after the Sun itself has changed, which makes them the most durable objects our species has ever made. Interstellar objects have already passed through this system from elsewhere, which means the crossing between stars is made routinely, just never by anything that intended to make it. And nearly everything we know about the nearest star system, all of it, the 3 stars and their orbits and the small tidally locked world circling the faint red one, we learned from here. By patient measurement of light that arrived on its own, having taken 4 years and a few months to reach an instrument on a small planet, the looking has produced results the crossing never could. So picture the sky, if the night where you are permits it. Somewhere low toward the south, in the direction of a constellation most people never learn to pick out, there is a faint point of light. It is not dramatic. It is not distinguishable from the 1,000 points around it without a chart and some patience, and the nearest of the 3 stars there is far too dim to see at all. What reaches an eye is a steady, ancient light that has been traveling for 4 years and a few months to arrive. That light left its source before any of this was recorded. The star does not know it is a destination. It has no idea that a species on a small world in a neighboring system has spent 70 years calculating the cost of crossing to it and found the bill unpayable. It simply burns, as it has burned for billions of years and will burn for many billions more, fusing hydrogen into helium in the patient way that stars do, shedding light in every direction equally, entirely indifferent to whether anything receives it. We are creatures of a few feet and a few decades, looking out at distances that consume centuries and at energies that would exhaust civilizations. And the remarkable thing, when you hold the whole ledger at once, is not the crossing. It is the looking. That something assembled out of the debris of an ancient stellar explosion can lie quietly on a warm world, in the dark, and feel the weight of a distance it will never cross. That is the part worth keeping. The star will be there tomorrow night, and the night after, unchanged and unbothered by any of this. 4 light years out, sending its light toward a world that will never quite reach it. There is a kind of peace in a distance that asks nothing of you at all. Let your breathing slow. Let the numbers go quiet. Sleep well and good night.